Okay, so the streaming has started. Before we start, just wanted to let you know that we will be showing sharing a feedback form for everybody. So you are supposed to answer it or like respond to it. So this feedback form will be with respect to the your what point of view or your what you feel about the quiz one question paper. Okay, so there will be some bonus marks. We are planning to have some bonus marks for students who are responding towards this feedback. Okay, so coming to today's tutorial session, we will be having a tutorial session for week 6 content and week 7 content. So I'll start with week 6 content, following which Livin will take over for the week 7 content. Okay, so let me just share my slides. Okay, so today what we are going to do is we'll take a string. Okay, let's say for example we are looking into this word which is cunning, and as in week 6 content you had looked into what suffix tries are, what suffix trees are, what suffix arrays are, and all of that. We will be constructing the suffix array, suffix tree, suffix array, suffix trie, suffix tree, suffix array, and the Burrows-Wheeler transform for this cunning word. Okay, then there was one other encoding. I'm not able to recall the name of that encoding right away, but we can look into that encoding. Okay. Uh, Now comes after this, whatever will be the Burrows-Wheeler transformation for this cunning word. Okay, we will use that Burrows-Wheeler transformation as the input, and we will use this as input to the inverse Burrows-Wheeler transformation problem, and we will generate the original string, which is basically this cunning string. Okay, so this will basically, what we will do is we will use cunning to generate this pwt. Once the pwt is generated, we will use this pwt to generate this cunning. So that way we can discuss both of the algorithms, both the Burrows-Wheeler transformation algorithm and the inverse Burrows-Wheeler transformation. Okay. So coming to the suffix tries, start with cunning. Okay. We are going to assume there is a dollar sign. Okay. Uh, at the end of this every sentence, every genome sequence or any sequence that's given to you for this particular topic, we will be assuming that there is a dollar symbol unless specified otherwise. Okay, at the end of the sequence. So for constructing suffix try, basically tries are, what it means is like we just expand everything into a path. Okay, so for cunning, what we will do is we'll start with every one of these suffixes, every suffix possible in this sequence, and we will generate the suffix try and add it as a path to the root. So let's say this is the root node. Okay, so the first suffix that we have is dollar. Okay, so we add dollar. Then we have G dollar, so we add G. Okay, basically this will be G. Okay, and then we will be having a dollar. Sorry, dollar. So this node will represent G dollar, which is basically the suffix from the. So I'm going to move this 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are the positions of the characters. So this path ends at, there is this dollar. We are adding dollar, so it ends at a leaf node consisting of dollar only, and this dollar symbol, this suffix is from the position 8. Okay, so we will be storing 8 also here. So now we have, if dollar is not there, we don't really need to store dollar, because we can just read the path from the root and we will get what suffix is being represented over here. Or we can just start from the number that we are putting over here. So from that particular number, we can just read whatever suffix is there and we'll get what the suffix is being represented at this particular leaf. Okay, so we start from this node. This is the 8. So we have dollar, so we are adding dollar, and hence this particular node stores the value 8, because the index of this dollar is 8. The position of this dollar is 8 in the string. Similarly, for the for G dollar, we add G, then we add dollar, and in the leaf node that we obtain, we are going to store the position of this suffix, which is 7. Okay, so here we will be storing 7. Then we have ng dollar, so we start with n. Okay, then we add g, then we add dollar. Okay, and we are obtaining ng dollar, and this suffix starts from this point with the position number 6. Okay, so we'll store the position number 6 over here. Okay, then this is basically what try means. You take a suffix or take any sequence and you just expand everything with one edge containing one particular letter. Okay, so that is what tries are. It's a very simple concept. Okay, so then we go for ing dollar. Okay, so we look for I first. Here I is not added to the root already. I is not a child of the root already, so I'm just going to add another I over here. Then we have n, so n, then g, then we have dollar. Okay, and again this starts from the position number 5. Okay, so 5 is being stored in the leaf node. Now comes ning dollar. So I'm going to add ning dollar, but when I'm starting, I can add a new edge over here, but I already have an edge to represent the node, the character n. Okay, so I will not be adding another edge for the character n. I'll just use this particular edge. I'll traverse along this edge only. So for the first character that we have, which is ning dollar, what I'm going to do is I'll look into the n, the first character n. It is already present, so I'm not going to add another edge with the character n. So I'll just traverse along this edge and go to the child of this root. Okay, so now here in n, I am trying to find for I is not a child of this n, so I'll just add another edge for I. Okay, and then I have ng dollar, so I'll just add then I have dollar, and this is again, this starts from the position 4. Okay, so I'll store 4 in the leaf. Now coming,
I have a question here.
yeah,
Why would you consider edges, whether they exist or not, only at the first level? So, for
no.
example,
If we have here, let's say, I'm changing this cunning dollar slightly. Suppose we have ng, nning. Okay. So when I am taking this particular suffix ng, the entire suffix, I am looking for ng. I'm starting at n, right? So I have an edge for n. I am going over here. Then I am looking for g. So I will be traversing this path along g. I will not be adding another node for g,
got
another
it,
edge
got
for
it.
g.
Okay, got
Okay.
it.
The reason why I'm just keeping on adding this ing dollar here directly is because when I add this node over here, it doesn't have any child. I already know that. So I don't have to look for a child which has the character n over here. So I just keep on adding. Does that make
Right.
sense? Yeah.
Yeah.
Okay. So the next one that we have over here, should I just go ahead with n and ng and ning instead of cu and ning?
Yeah, yeah,
I
that
think
would
this
be
will be
nice.
better. Yeah.
Yeah.
So let's take this ng and an ing instead of cu and an ing. So this one again, I'm going to note it as 1, 2, 3, 4, 5, 6, 7, and 8. Okay, these are the positions of the characters. So we had we had already built the try up to ning dollar. Okay, so now we'll look into n and ing dollar. So NNING dollar. So what happens when I start with NNING dollar? I start with N. So we look for the child of the root which is containing the character N. So it is already there. So we traverse this edge which has basically it's not a child but an edge. Okay, an edge going from the root containing the letter N, or the weight of the edge will be the letter N. Okay. So there is an edge with the letter N. So we just traverse along this edge to this particular child. Now I'm going to look for the character N for its from on the edges coming out of this particular node. So here we don't have the character N anywhere, right? So I'm just going to add an N over here. Okay. Now this particular node doesn't have any children. We already know that, so I can just keep on adding the characters. So here I will be adding I first. So N and I, then I have an N, then a G, then a dollar. Okay, and now this suffix is starting from the position 3. Okay, so we'll have the position 3 over here. Next we have GNNING dollar. So I'm going to look for the character. Okay, let's write over here GNNING dollar. So we'll start with the character G, and we will look for the character G among the edges or among the children of the root, basically among the weights of the edges on the other number for the representation, whatever we are using to represent the edges. Okay, so we have an edge for the character G. So we will traverse along this particular edge and we will reach this node. Okay, so from here we can just we will look for the character N now. Now here we don't have the character N, only the character dollar is there. So there is no edge with the representing the for the character N. So we will add an edge for the character N over here. Okay. So now this node doesn't have any children, so I don't have to look for more children. I can just keep on adding them, adding these children. Okay. So I'll just keep on adding these children so that we have G, and then I'll add N, then we can have I, then we can have N, then we can have G, and finally we can have. Okay, so this again starts from the position 2, so we'll store the value 2 at this particular position. Okay, so then finally we have ng and an ing dollar. So we'll look for the character n among the edges from the root. We'll start from the root. We'll look for the character n among the edges from the root, and of course there is a character on the there is an edge on the character for the character n. So we'll traverse this edge. We reach this particular node. Then we have G. Okay, so now we look for G among its children. Okay, and we have an edge for the character G. Okay, so we will traverse along this edge and we will reach this particular node. Okay, now we were going to look for N among its children, but G is only having the character dollar. This is basically dollar. Okay, N is not there, so we will add an edge over here for the character N. Okay, and this is a new node, so ngn. Okay, so we will just it doesn't have any children, so we can just expand everything out now. Okay, and so ning I, then n, then g, then we have dollar. Okay, finally this starts from the position 1. This is we will have the position 1. So this is the suffix try. Okay, do you want me to write it over here nicely? So we have a dollar.
I think this is quite visible.
Okay,
should not be an issue.
Okay, fine. This is the suffix try. Okay, now what is the problem with suffix try? We have a lot of edges with the degree 2. Degree 2, you mean what? We mean what? One node will have a out degree of 1 and the other node will be having an in degree of 1. Okay, so this kind of nodes are these kind of edges are very prominent in suffix tries. So as you can see here, like for example, this particular edge is starting from this node, but there is only one child, then this no edge is having one child, this edge is having one child, and so on. Okay, so there is a single and path, like a path kind of a thing, where every edge on this path is just having one starting point and one ending point. There are no childrens or anything. There are no nodes with more than one children in along this path. Okay, so what trees do is, suffix trees do is, instead of having this long path with multiple nodes and multiple edges, it just compresses the characters for each of these edges into one particular string and uses that string to represent one edge. So what we will do here is, for it, we will start with the root. Okay. Now let's see for the dollar. For this particular dollar edge, there are no paths, no children, nothing. So we'll just add it. Okay. So we have the dollar and we have this 8 over here. Now what happens? So this is the suffix tree. Okay. Not to confuse with suffix tries. This is suffix trees. There is a huge difference between suffix trees and suffix tries. Okay. So the suffix tree, this is suffix trees and this is suffix tries. Okay. So what happens? We start from the root, we add this dollar and we get this 8. Now here we go to G. So along this edge, if we look, this particular node is having 2 children. So we should be having that node. Okay, we don't need to remove that node. So we will have a node. We will have an edge for the G. So we will have a node here. Now from this particular node, notice this path. Every node along this path is just having one inner edge, one outer edge, one parent, one child, one parent, one child. Okay, so we will just compress all of this and just keep this particular leaf node. Okay, we will have the leaf node. Everything else we will remove. Okay, everything else we are going to remove, and we will be compressing all of this entire list of characters into one string. Okay, so that is what we will do here. We will have one long edge with the characters N, N, I, N, G, dollar. Okay, so we added all of the characters as one particular string to this for as a weight of this edge. Okay, now we will just have the leaf node which stores the value. Okay, now what we do is,
why would you include dollar also? Dollar is only 1 degree.
yeah, dollar is also the same thing, right? Not dollar, the edge for the dollar, the node, the parent node of this particular edge is having one child.
Oh, got it. Sorry, my mistake. Yeah. It's okay. Yeah.
Okay. So now
Yeah.
again, coming to this particular path, there is nothing, just one edge with one parent, one child. So we don't have anything to compress. We'll just add that edge with the representing the term dollar and having the value 7. Okay. Now coming to this particular edge, again we have this node is having multiple children, so we can't compress this. Okay, so we'll add this node as a child to the root. So we have N over here and we have this child to the. Okay, so now what happens? Every path from this, let's consider this path. Okay, for this particular path is just having one single, this is a single path. Okay, there are no children. Every node along this path have exactly one child. So we will compress all of these nodes into one edge. Okay, we will compress all of this into one edge, and that edge will store the string representing all the characters from here to here. Okay, so what we will do is, we will have one single long edge which will be representing the characters N. So we have N, then we have I along the path, so we will have I, then N is there, so we will have N, then we have the character G along the path, so we will have G. Finally we have dollar, so we will add the dollar. So what we are doing is, we are just removing these round things. Everything else we are just connecting. Okay, so this is what we are doing. This is a trick: convert suffix tries to suffix trees. Okay, just remove the round things and just connect the edges. If there is no branching, okay, if there is no multiple children, then just connect the edges and remove the nodes in between. So what happens is, this is what we do, NING dollar we get, and at the end the leaf node is having the value 3. Okay, then coming to this particular edge, here we are having a branching. Okay, so we will need to add this edge. Anywhere we encounter a branch, that is a node is having multiple child, that node must be there in the suffix tree. So we will be having this node, so we will need this edge also. So we will have G over here and a node over here. Okay, so now this is just a one edge path, so we don't have to do anything. I'll just add this for dollar and the value is 6. Okay, now this path is again the same condition. Every node is having just one child. Okay, so we'll remove these circles over here and we'll connect their edges. Okay, so this is what I'm going to do, just connecting these edges. Okay, so we will have this edge over here, long edge, which will have the characters N first, then followed by another N, followed by I, sorry, this is I, followed by NG dollar. Okay, NG dollar. Okay, this is having the value 1 in the loop. Okay, now coming to this particular path, we have I over here, but there are no branching. Every node along this path is having just one child, so we can just remove these blocks and or square circles and just connect it. So again the same thing, we will have one long edge with the characters I, N, I, this I, followed by this N, followed by G, I, N, G, followed by dollar, and the leaf node has the value 4. Okay, now coming to this path, we have ING dollar. Along this path, we don't have any branching or anything, so we can just follow this path. We again, we can just connect all of these. There are no branchings. Every node is having one child. So we will just start from the root and we will connect these edges, remove the circles, and we'll connect the edges. Whatever edge we will get, we'll write it nicely. Okay, so this is, we remove these circles, connect the edges, and write the edge nicely. That's it. Okay, so add the edge. Then we have ING dollar, ING dollar, and finally the value 5. So we will have 5. Okay, so this is what is called as a suffix tree. This is suffix trie. Okay, the difference is basically this I and E. Okay, so don't confuse between tries and trees. So this is a suffix trie and this is a suffix tree. If you look into a PYQ question, I think last term or its previous term, there was a question to find the string from the suffix trie. Given a suffix trie, you have to find what string was used to construct the suffix trie. Basically the reverse. Any idea on how to do that? How do you obtain the string from the suffix trie or the suffix tree?
Take the possibly takes the number 1 and then just go back from there.
Exactly. You take number 1 and you just go back from here. You take number 1 over here and just go back. So dollar G. Let me just write it down. I'll start from 1 over here. Okay. So we have dollar. We encounter dollar first. Then we have G. So we G. Then there is N. So N. Then there is 1. Sorry, I. So I. Then we have N. So N. Then again N. So N. Then its parent has the value G. So G. Then N. So and you get NG and NING, which was the original string. Okay. Similarly, from suffix trees also, if you go back, to obtain this, you just go back from 1. So if you start from the leaf node 1, you have dollar G, then NN, sorry, NI. So NI, then we have NN. So previous to that we have G. So G, then N. Okay. So this is how you can use suffix trees and suffix tries to obtain this particular thing. Okay. Then next is suffix arrays. Okay. So what was our string? NG NN
ING.
ING dollar. Okay, so this was the string. Now to construct suffix arrays, the best way is to just write 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what you should do for suffix arrays is, okay, so dollar is always considered as a character which comes before a in the alphabetical order. Okay? That is universally accepted for this particular topic. Okay, so whenever it comes to the topics,
Dollar is a zeroth character.
yes, it's considered as the zeroth character. Okay, so now what we are going to, now what I mean by zeroth character is when you are arranging everything alphabetically, it is the zeroth character. A is the character number 1, dollar is character number 0. Okay,
Right.
so what we are going to do is we are going to find every possible suffix from this. So we have ng, nn, ing. First of all, I'll discuss what is the actual method to solve this, and then I'll discuss what is the easiest method to solve this. Okay. So the actual method here is we have ng, nn, ing. So what we are going to do is write every suffix, every possible suffix. Okay. Ng, nn, ing dollar. Then we have gnn, ing dollar, gnn, ing dollar, then NNING dollar, then NINING dollar, ING dollar, NG dollar, G dollar, and finally dollar. So this is 1, 2, 3, 4, 5, 6, 7, 8. This much is clear, right?
Yes.
So now what we are going to do is each of this is a string. Consider each of this as one word. Okay.
As one?
One word. So this is one word. This is one word. This is one word. Okay. Basically, these are words given to you. Okay. And we will be alphabetically sorting these words. That's the idea. Each of these is a word. Okay. So what word will come first? Alphabetically, as I already said, we have dollar, then we have A, B, C, D up to Z. Okay. So alphabetically, so which of these strings or which of these word will come first? You can consider it as string if you want to go in more technical language.
Eight will come first. 8 will come first.
Exactly. So we'll write 8 first. 8 will come first. Then which will come first? So let's go A, B, C, D, E, F, G, G.
2,
so
2 and 7.
2 and 7. So out of these 2 and 7, we have to again short it because we are doing it according to a dictionary order. So 2 will come first or 7 will come first. So we'll go to the second letter.
7.
So what is 2?
7 will come. Yeah.
Yeah, 7 will come. So why 7 is coming? I'm going to write it over here. GNNING dollar, right? We have GNNING dollar. Then we have G dollar. Okay. So now the first letter is the same. So we'll go to the second letter. The second letter is N and dollar. So as I already explained, dollar will come first. So that's why G dollar will come first. What is G dollar? The name of this G dollar, we are using 7. So 7 will come first and hence we'll write 7. Okay. So next what will come? Okay. So 8 is done. 7 is done. Now what will be the character?
6.
Why 6? 2 is there.
NG. Oh yeah, sorry. 2 is there, of course. We
2
have
is
not
there,
done 2.
right? Yeah. So we'll add 2. Okay. So this is done. Now what will come? So
6
we have
will come.
A, B, C, D, E, F, G, H, I, J, K, L, M, N, G, H, I, right? A, B, C, D, E, F, G, H, I. So I precedes N. Okay. So what is, so we don't have I here, we don't have, this is N, this is N, this is I. Okay. So we will be using this. Okay. So 5 will come next, right? Hello?
Yeah. Can you not hear me?
Yeah, I can.
Hello?
Yeah. Yes. Yeah. So 5 will come next. So we'll add 5 to the suffix array and we'll remove the string for the 5th one. Okay. So what else is remaining? Now it is getting a little complicated. So let me write it over here again. N G N N I G.
Now you can just go from bottom to the top. So it will be 6, 4, 3, 1.
Why?
Because
And
the shortest string, because the strings are all the same, in the sense they all
okay.
have the same character, the shortest one will come first. Because the
Not
dollar will
necessarily.
come first in number 6. The dollar is at the third character in number 6. It's
But
at the
G
sixth
will come.
character.
See, let me just write here. Let me just write. One second. Okay. NING dollar. This is 3. This is 4. This is 6. Okay. So 6 we have NG dollar. Okay. So from here we have N is the same. So we'll go to the second character. Second character G will come first, right? G precedes I and N.
Right.
So we will have G first. So
Right.
either this or this. Okay.
Dollar will
So
come first. Yeah.
the third character will be dollar, and this is
Yeah.
N. So we will have 6 first. Okay. You were right.
Right.
We will have 6 first. So we'll remove 6. Okay. Then we have 1, 3, and 4. Among this, again, the first character is same, which is N, but the second character G precedes
One will
N
come.
and I.
Right.
Yeah.
One
So
will come first.
we will have 1. So we'll add
Then
1.
4, then
And
3.
one.
Okay.
Then from this 2,
Four.
we have N
4.
is the same. So yeah, I will precede N. So 4 will come. And then 3 is
3
coming.
will come.
Okay.
Okay.
Right. So this is a way to construct the suffix arrays. Now another method is what you can do is sort these letters. Okay. For every letter you have this 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So now if you sort these letters, which character will come first? Dollar. Okay. At the character 8. So we'll write dollar first. Okay. Dollar at the position 8. Okay. Next, what is coming? The character G. So we have G at 2 and G at 7. So we will just write G at 2 or G of 7. These two will be taking the next 2 positions. Okay. Then we have the character will be I, right? Yeah. So the character
Yes.
I will be at the 5th position. So at the 5th position, so I'll be having the character I over here. Okay. Then we have 1, 2, 3, 4. So 4 N's. So there will be 4 N's over here. And we will just check out what will come first. This is 1.
Can I suggest a very simpler method, the same method but in a simpler way?
Yeah, go ahead.
So can you just write NG, dollar somewhere else as well?
Yeah, sure. G N N I N G
dollar, and just write
Yeah.
1 to 8 above or below it.
1, 2, 3, 4, 5, 6, 7, 8.
Oh, so now we go right to left. Dollar is the smallest. So we write
Yeah.
8 first, strike it out.
Okay.
Just strike it out.
Done.
Okay, now G is next. Right to left, 7 is first, 2 is next. So you write 7 to strike them out.
Okay. Okay.
Then I is smallest, and that is 5
Okay.
right to left. So write 5, strike it out.
Okay. Okay.
Then N is smallest now. You'll have 6, 4, 3, 1.
Okay.
Okay.
6,
But
4,
4, 3, 1.
3, 1. This is not the
3, 1.
right way.
Yeah, I know. I'm just wondering where I went wrong here.
Where you went wrong here is you are just reading it from the back. But it is
Yes.
possible that the front can come first because this character will be a smaller character. I can have an A over here.
Okay.
Okay. So
Well,
what
very
you
good
should do
learning. Okay.
is, yeah, this is how you learn actually.
Yeah.
So yeah, so N1, this is N3, then we have N4,
Right.
and we have N6. Okay. So
Yeah.
what you just need to do is for each of these sets, you need to go to the second character, the character following it. So we have $8 over here. Okay. So we go to G2 and G7. I'm not right. Okay. Let's write $8. Then we have G2, G7. Okay. So we'll go to G2, G7. Okay. Now what is 2 plus 1 is 3. So we have N. 7 plus 1 is 8. Okay. This is dollar. Which one of these is smaller?
That's why it comes first. Okay, got it.
Okay.
7 comes first.
Yeah. So dollar is smaller, so that's why 7 comes first. So we have G7 and G. Okay. Then we have I5. Now I'm going for the same thing. N1, N3, N4, and then N6. So we have 1 plus 1 is 2. So G. This will be G. Okay. And 3 plus 1 is 4. So 3 plus 1 is 4. So the fourth character is N. So we have an N over here. Then we have an 4, which is 4 plus 1 is 5. Fifth character is I. 6 plus 1 is 7. Seventh character is G. Okay. So we have two G's, N and an I. So we are going to short it. So we have G and a G. So these G's will come first. So I will have N1 and N6 here. Then I will be having an I and an N. Okay. So this will be N4 followed by N3.
Got
Okay.
it.
Now
Okay.
remaining is N1 and N6. So we'll just sort N1 followed by N6. Okay, so now we have already looked into the second character plus 1. So we'll do plus 2 now. So 1 plus 2 is 3. So we have N over here at the third character. 6 plus 2 is 8. So we have a dollar for this character following this okay. So we will
Right.
again short it. So we'll have dollar first and then N. So we'll have N6 first followed by N1. So we'll have $8, G7, G2, I5, N6 followed by N1. Then we have N4 and N3.
N3. Got it.
Okay. So finally, this
Yeah.
is not the suffix array. This is not the suffix array. What is the suffix array? Write the numbers. You just take the numbers and you write it in an array. Okay. Just like
Okay.
you write in Python lists. You take the numbers and write it in an array kind of a way. Okay. 8, 7, 2, 5, then 6, 1, then 4, 3.
3.
This is
Got
the
it.
suffix array. Okay. Now there is
Great.
another way out. We'll discuss
Okay.
now. There is a previous year question. Given the suffix trie or the suffix tree, can you find the suffix array? Let's say we'll take the suffix tree because it's looking clearer here in this particular diagram. From the suffix tree, how will you compute the suffix array? This was
So
a question in a previous year question.
logically speaking, you can look at the shortest edges and then mark them first. So 8 will come first.
Okay.
7 or 5, which one should come first? Let's say
No.
7
What?
comes first. So
Why?
dollar G dollar, right?
Yeah.
8 7 ing
Okay.
dollar, then is the third shortest. No, 6 is ng dollar is 876 5. No. There's something wrong.
If you are taking the shortest paths, then you will end up with the reverse of the whatever
Yeah, I
you are
just
having.
realized that. Yeah.
Okay.
So okay, no, I
So
get
what
it.
you
So
should do is,
we will count the number of characters there. So 8 7
okay.
uh 8 7
Why
ng
don't you think
dollar.
about this and we'll discuss in the next session. This is a PYQ
Okay,
question.
okay.
Think about this, or you can post if your solution in the chat, Google chat, or you can post in Discourse, or if you're not getting the solution to this, we'll discuss in the next session.
Sure, will do.
Okay. So the question is, given the here's the question. Given the suffix tree, trie or tree, whichever is convenient to you, find the suffix array. Okay. This is the question. Okay. Okay. So now we'll go to the Burrows-Wheeler transformation. So we have, what was the ng, n, and ing. N, G, N, I, N, G, dollar. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, there is one more encoding method. What it does is, I don't remember the name. I'll tell you the name in the chat box or before this ends. So what we do that in that is, it's called run length encoding. Yeah, it's called run length encoding. Okay, so run length encoding. Okay, what it does is, you take n, how many occurrences of n are consecutive to it? None. So we take n and we write 1. Okay, so basically one occurrence of n. Then we have g, which is occurring once, so we write g1. Okay, then we have n twice. Okay, so we write n 2 times. Okay, then we have I, which is occurring once, so we have I1.
What
N
you
is
write? N1,
occurring.
N1, G1, N2, N1.
This
No?
is a form of encoding this particular string.
Oh, it's a
There
string
are
encoding, not
multiple.
a character encoding. Okay, okay. Got
No,
it.
no, 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 no. It's a string encoding. Okay. So
Okay.
we have n representing n. There are only consecutively, we are having just one n character. So we have n followed by the character 1. Then we have g followed by the character value number 1, because g is occurring only once. Okay. Then we have n 2 times. So we have n2. Okay, then I is occurring once, so we have I1. N is occurring once, so we have N1, G1, and $1. Is
Oh,
this clear?
got it.
For example, let's say we have uh, uh, T A C T. What will be the run length encoding for this now?
M1, A3,
A3,
T2,
T2.
T2, A1,
No, this is A1. Yeah,
C2, T1,
C2, T.
T1.
Okay, this is, yeah, this is what is called as run length encoding. Okay, so this is everything about run length encoding. So now we'll go to
Okay.
the Burrows-Wheeler transformation. Okay, so we have ng, so what Burrows-Wheeler transformation does is, similar to suffix arrays, what you have to do is, you have to short every possible string from this. So what we are going to do is, we will use it as a circular string. Okay. So we have ng, and first of all, the actual method followed by the easiest method. Okay. The method that I use. Okay, so I'll go with the method given in the book and in the slides and everything. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'll start with what are the strings that you can have from here. So we have ng, nn, ing, dollar. Then we bring the dollar to the first, okay, and then the remaining string. Okay, ng, nn, ing. This is called shifting by 1. Okay, left shift. This is left shift or right shift, I don't know, but it is shifting. Okay, so we are shifting this character backwards. Okay, so we are taking
Right
this
shift.
g and going to the backwards. So we
It's
have
right.
g dollar. Sorry,
It's right shift.
hello,
This is
g
right
dollar
shift.
and
Right,
g.
right shift.
Yeah, yeah, yeah. This is right shift. Okay, this is right shift. N G N I N. Okay, then we bring n to the first. So we have n g dollar, n g dollar, then n g n
NNI.
I. Then I comes to the first. We have n g dollar, n g n n. Then n comes to the first. N I n ning dollar, NING $NG. Okay, then NNING dollar NG. GNNING dollar W. Then W. Sorry, this is N. Then we have N, G, I, N, G dollar. Okay, this is basically the first one. We don't need repetition. We can just use one of these. Okay. So what we are going to do is again similar to suffix arrays. We will short these. We will consider each of these is one string. Okay, each of this is one string, and we will sort this. Exactly similar to what we did with suffix arrays. So how do we do that?
So first will be dollar.
So let's start. What will come first? Obviously, we
Dollar.
have dollar $G and I and then GN. So dollar will come first. So we'll write dollar. So dollar $NGNN ING. Okay. Then what will come?
It will be G dollar. Yeah, second one.
We have G dollar. We have G and G. So G will come first. So G and G dollar. So obviously G dollar will come first. So this is already done. So G dollar will come first. So we'll add this one. So G dollar NGNN IN. Okay. So then GN. So GNN ING dollar N. I don't want to rush. Let me know if you are confused or if
No,
this
no,
is clear.
this is good.
Yeah. So now what will come next then?
ING.
ING. Yeah. So ING dollar NGNN. Okay. Now what will come next? We have
NG dollar.
NG dollar. So NG dollar NGNNI. Then
Then you have NG
comes
and NG and an ING dollar.
NGNNING dollar. Okay.
Then you have
Then we will
NING, NING,
NING dollar
NGN.
NG followed by NING dollar WG.
NG, NG.
Okay.
It's not W. It's NG.
Sorry. This is NG. Okay. So once this is done, basically what you are going to do is you will create a string. We'll create a string by what we will do is the Burrows-Wheeler transformation of this string, okay, is equal to take the last character of each of these,
Okay.
okay, and just keep append it. So you take the last character of the first one, which is G, so we have G. Then you take the last character of the second one, which is N, so you add N. So then the the last character of the third string, which is N, so it comes N. Then the last character of this string is N, so this will be N. Then we have the uh, last, this is I. Okay. Last character of this string is I, so we have I. Then we have the last character of this string is dollar, so this is dollar. Then we have the last character of this string is N. Last character of last string is G. Okay. So this string, whatever string you obtain, this is the Burrows-Wheeler transformation of the original string. This is basically an encoding of the original string.
Okay.
Okay. Hello.
Got it. Got it. Can you hear me?
So yes, I can hear you. So this is
Okay.
the Burrows-Wheeler transformation of the original string. Now the question is, now to do it faster, I told you that there is another way to compute this Burrows-Wheeler transformation fast without actually performing all of this. Okay. For that, what you will need is the suffix array. Okay. If you have the suffix array of a given string of this NG, NN, ING dollar, if you know the suffix array of this, then can you compute the Burrows-Wheeler transformation in order of n time complexity? See, this is order of n squared, right? You have to go through everything.
Yeah.
Okay, this is order of n squared. So if the suffix array is given to you, you can compute the Burrows-Wheeler transformation of the string in order of n. There is an algorithm which is actually a very fast and easier way to find the Burrows-Wheeler transformation. So do you want me to discuss the algorithm right now, or do you want to try it and then you want to look into it? There is a previous year question on this particular.
Then I will try it myself.
Okay, fine. Try it. If you don't find the solution, then I'll let you know. Okay, there is an order of an algorithm. Okay, I
Okay.
think. Okay. So, anyways, now coming to the inverse Burrows-Wheeler transformation. So, inverse Burrows-Wheeler transformation, what we have is, yeah. So we have what this inverse Burrows-Wheeler transformation does is, it's the decoding method. This is the encoding method. So we are encoding this string to this. So now we are going to decode it from this particular encoding to this this one. Okay. So the Burrows-Wheeler transformation is G triple N. So we have G triple N followed by I dollar NG. I dollar NG. Okay. So what we are going to do is, in this inverse Burrows-Wheeler transformation, we will write all of this, up to down manner. Okay, G and N. Then we have I S N
Dollar. That's
G.
dollar. It's the dollar, not F.
Yeah. I dollar NG. Okay. So now what we will do is, we will short these characters. Okay, we will short these characters. Which character will come first? Dollar precedes every character. So dollar is the character which will come first. So I'll leave some space out here and I'll write dollar here. Okay. Then which character will come? So we are done with dollar. Then what we have? G, we have 3 N's, then I, and then G. So which character will come first then?
G.
G. So we have 2 G's. So I'll write 2 G's over here. This is G. This is G. Okay. Then which character will be there?
I.
I. So I have I. Then we are having 4 N's. So I'll write 4 N's. 2, 3, 4. Okay. So now what we are going to do is, for these multiple cases, the ones with these repetitions, we are going to number this. This is G1, this is G2. This is N1, this is N2, N3, and this is N4. Okay. Here also I am going to number it. This is G1, this is G2. This is N1, N2, N3, and N4. Okay. We'll start with dollar. Okay. So what happens? Let me just look into it. Dollar. Yeah, we will start with, there are 2 ways over here. Okay. Both, I will be discussing both the ways. I'll start with, this is row number, this is column number 1. Okay. This is the column number, first column. Okay, this is the second column or the last column. Okay, so what we'll do is, we'll start with the first column and we'll compute the string. The second method we will discuss is from this. We'll start from the second column and we'll compute the string. Okay, so the first way is, let's start with the first column. We have dollar. We'll start with dollar. So dollar is pointing to G1. Okay, so we will write dollar. We will write a dollar. Then it is pointing to G1, so we'll write G1. Okay. Now we'll go to G1 in the first column, which is over here. Okay. So G1 is pointing to N1, so we will write N1. Okay. N1. N1 is pointing to I. Okay. N1 is pointing to, N1 in the first column is pointing to I, right? So this N1 is pointing to I, so I will precede N1. Okay. Now I in the first column is pointing to N3. Okay. So we will have N3 over here. Now N3, so N3 will precede I. Okay. So now N3 in the first column is pointing to N4. So N4 will precede N3. Okay.
Right.
Yeah. Now where was we? Where were okay?
N4 to
So
G2.
N4 in
N4
the
to G2.
first column. Yeah, the G2. So N4 in the first column is pointing to G2. So G2 will precede N4. Okay. Now G2 in the first column is like the corresponding value in the second column is N2. So we will have N2. Now what is N2 in the first column is pointing to dollar. So dollar we have already added, so we can just stop. This is our actual string. If we remove these numberings over here, we have NG and NI and G dollar. Clear? Is this clear?
Yeah. Yeah. That's great.
Now we will look into how we will start from the second column and go to the first column, because some get confused. Okay. Okay, so we'll start with the second column and we'll go to the first column. So we have dollar over here. So we will not write dollar. We will, what is dollar pointing to? Dollar is the second column. This is the last column. So we will write dollar at the last. Okay, so we will not write dollar. So we are starting from here. We are not writing dollar. So now dollar is pointing to N2. So N2, we will write N2. Okay, N2 in the second column is pointing to G2. Okay, so here it will succeed. Okay, so N2 then G2. So we will N2 will be followed by G2. Okay, when we are starting from second, it will follow. Okay, start from second, then don't write dollar and succeed. Okay, everything will every character will succeed the previous character. Every new character will succeed the previously added character. Okay, so we have N2. N2 is corresponds to G2 over here. So G2 will follow N2. Okay, then G2 in the second column corresponds to N4. So N4 will succeed G2. Okay, now N4 in the second column corresponds to N3. So N3 will follow N4. Okay, then N3 in the second column corresponds to I. Okay, so I will follow N3. Okay, now I in the second column is corresponds to N1 in the first column. So we will have N1 following I. Okay, now N1 in the second column, we have G1 at the corresponding position. So G1 follows N1. Okay, now G1 in the first column, second column corresponds to dollar. So we will write dollar and we are ending because dollar. We are done with it. Is this clear?
Yeah.
So this is important. If you are starting from second column, this is what you do. But if you are starting, I'm writing over here. If you are starting from the first column,
Go right to left
yeah, we
and
will
start with
write,
dollar.
yeah, write the dollar. Start with dollar. Go right to left. This is every character. Precedes the previously added character. This one is you should go left to right. Okay. So this
Yep.
is basically the content for week 6. Summary of different problems you can get from week 6. Actually, you can have lot of variations in this, like um, how to compute a suffix array from the suffix tries and all these interchanges that we discussed, right? So all of that you should look into those kind of questions. Okay.
So where
So
is
this
it?
is the
Where can I
content.
practice more content from? So apart from PYQs and assignments, which is a good place
These
to?
So the thing is, there is no specific. This is a degree course. It's an advanced course. Okay, so these courses are basically they don't have any specific problem-solving books. So, for example, for this particular chapter, what you should do is just take some random strings and do all of these four five things. So once you do all of these four five things, to be honest, even I wasn't that efficient in computing these suffix trees, suffix arrays, and everything until I started preparing questions myself. Okay, so when I was preparing questions, I had to solve them, and I saw different kind of connections between these different data structures. Like for example, this suffix Burrows-Wheeler transformation, suffix array to Burrows-Wheeler transformation. I haven't read it somewhere, but I found it on myself when I was like solving it. I was preparing these questions and I saw that, hey, this is an easy way out to find the Burrows-Wheeler transformation. When this comes with very lots of practice. That is actually how I learned. I am not sure if you can find any books on that, but that is how I learned these problems on this subject in this course. So actually, I can't help you in that way because I don't have a book from where I have solved these problems. I learned these problems by preparing these questions only. When I started preparation of these question papers, and when I solved multiple problems to like see which question should go for the question paper, which should not go for the question paper. I had to prepare multiple examples, multiple questions, right? So when we were doing all of that with that kind of practice, that level of practice, when we did like when I solved like tens and 15 20 questions from one particular topic, that is how I practice, that is how I learned. I don't know what else to tell you.
That's
Okay.
good. I mean, what I also do is I trying to find other courses at a degree level
Yeah,
in other universities and I see their questions. So
yeah,
sometimes
that
that
is
also
actually
helps.
a good way. That is a good way. So for this particular week, I'm keeping the annotations and I'll share the slides. Okay.
Okay.
Okay. So I'll stop sharing and Livin can start with the week 7
Thank you.
content.
Yeah. Okay. Share my screen. Okay, screen is visible. Am I audible?
Yes. Yes, it is.
Yeah.
You're audible.
So this is just a demo notebook of demonstrating how uh, we do k-means clustering and soft k-means clustering. Right? So this basically we are starting from a random data set. So it's a blob data set with some two Gaussians. You can say we are generating sampling from a mixture of two Gaussians. It's that how it is. These data sets. So this is the version data set, and we can see the class labels highlighted in two colors. Right? And also we are so in the k-means clustering algorithm, we initialize the centers, right? We randomly sample any 2 points from this cluster, or this data points, the whole data points, and then mark them as our cluster centers initially. Then we go on updating the centers as you know, right? So this is the hard k-means that we have here, right? Yeah. So first, what we'll do is we find the distance. So this linear norm is basically the L2 distance of the Euclidean distance. So using that, we are measuring the uh, distance from each cluster. So we have the centers over here, which we have generated randomly from here. Then we are finding the distance. So this is the difference, and then after difference, we are finding the norm, which is basically this thing is basically the Euclidean distance. Then we are finding the cluster with which the data point has minimum distance. That's our prediction. So, and then we are talking responsibility, we say in these terms. So, which is basically a one-hot encoded vector for each cluster. So, which cluster does the data point belong? So, that is so responsibility. Like for each cluster, we say how much does the data point belong to that particular cluster. So since in hard k-means, what it will be is just the one-hot encoding because it will belong to only one cluster at a time. So it will be a one-hot encoded vector index. As you can see, so this is the initial data points, and then after each iteration, as you can see after the one iteration itself, it is almost at the center. It is kind of fitted for this data set, right? And if you see, the initialization also has an effect on how this algorithm works, right? Let's see. Okay. Okay, let's try with a different one. Let's try with this one. This seems to be also fine. But the way it proceeds is slightly different, as you can see. The previous one, it was almost close to each other, and within the second iteration itself, it is already at the point. But here it is gradually growing, as you can see here. After almost 3 iteration, it is at the right point. No, after 4 iterations, yeah, you can see these points, these 3 points are not here in this one. So after 4 iterations, it's almost the same, right? So that's how the initialization matters. Sometimes it might not even, when the centers are very close to each other, sometimes it might cause some issues over there. Mistaken. That's fine. Okay. Let's take this example. I'll just working. Okay. So what actually happens is the centers are close to each other. Sometimes all of these data points might be associated with one of the cluster.
Only.
Uh,
Right.
Because of
Because it's
that,
not able to differentiate
then
between
there
them.
might be, sorry,
Because the algorithm, the way it works, it starts favoring one point more than the other.
Ah, so what happens is if all the data points are assigned to one cluster and one data point is except this assume this data point is selected for a center and this is selected for the other center, what will happen? All the data points will
Everything will
be
go to this
related to
one.
this one. Yeah,
Yeah.
so those kind of scenario might happen. So initialization is also important in that. So that's why modern algorithms they use something called as k-means plus plus initialization, which essentially what it does is it first chooses a point randomly and then chooses a point which is far away from the uh, current point in that system. So if it chooses this one, it won't choose this one as a second point. It will choose this one as a second point, which is farthest. And for the third one, it will choose a point which is further away from both of these points. Maybe this one, which has to make some distance from both of these points. So those kind of initialization kind of ensure that uh, we do not end up in those kind of scenarios, right? So that's it for the hard gaming. Then we do a little modification for the soft gaming. So the only modification that we do is instead of after computing the distance, instead of computing the responsibilities by using a one hot encoding, which essentially does chooses only one with the match, we are doing a soft match instead of doing that to get the responsibility. Right. So with that, uh, we'll be getting. Yeah. So you can see here, right? So let me initialize using this initialization part. Here you can see how the initialization happens. So this opacity, the change in that opacity that you see is basically how strong is the responsibility. So those certain nodes that are at the middle point tend to have this low responsibility for that particular class, right? Because kind of these are kind of very equidistant from most of this, so it will have half responsibility in both classes. That's how the algorithm proceeds. Other than that, implementation wise, only difference is instead of a hard max, we are using soft max. That is the only difference between hard k-means and soft k-means in terms of the implementation. And the probability. So instead of updating based on the hard probability, they are updating based on the soft probability. So that kind of ensures how we can tweak this algorithm. So let's see how the parameters of this soft k-means affect the thing. So we have something called as beta. So I have kind of a re-implementation of the same stuff over here, uh, but with a different visualization. With by changing the different values of beta, we can change how the beta converts to, right? So that is the, let me try different values. Right. Yeah. So increasing this beta kind of makes it very hard. That's what you can see out here, right? The resistance boundary seems to be very hard around here. And by decreasing the value of beta, we can ensure that the decision boundary is also kind of very soft, not at a very hard line, but gradually changing over there. So the point of convergence also, so by setting it very low, it might totally blur out the decision boundary. As you can see, this kind of points. So this is kind of how we measure the confidence as we want. So we want to predict whether uh, we used to have certain thresholds, right? Sometimes before classifying. So we can say this point certainly belongs to this class. But this point, with this kind of adjustments in the beta, it's kind of threshold we want to set. So this kind of prediction gives us an estimate of how good is this point. For example, this point might not be very good at this cluster, belonging the green cluster, right? The hard k-means will kind of gives us the hard probabilities, where the soft k-means kind of gives us a way to control how you want to make the uh, uh, boundary soft. So that is one thing that soft k-means gives us, that model. Usually in the k-means, it will be just a decision boundary, and this will be this class, and that will be this class. We'll do a hard k-means on the inference step also, right? In the soft k-means, by adjusting the parameters, you can adjust how is the decision boundary. So since this overlap, when you see there is more overlap in the data set itself, you can decrease the beta so that the decision boundary kind of matches the amount of overlap between the data. Right? So that is one thing about the soft k-means.
So is this available to us, the code?
This notebook, I think it is not shared with you. Maybe I'll share it in Discourse. I'll make a Discourse post and I'll share it.
Yeah, thank you.
Can we upload files? I think Discourse might not be supporting it. I'll share it in Discourse.
Discourse, you can share the link, and anyone who has a link can access it. You can put the sharing like that, so you don't have to upload the file.
Okay, maybe I'll upload it in Colab and then maybe I'll
Yeah, in Colab, right? Exactly.
Yeah. Okay. Any doubts you have?
I know this. We have covered a lot of this in MLT earlier, so it's a
Okay.
bit easier to absorb than the rest of the course.
Okay.
So thank you so much for explaining
Okay.
it.
Yeah.
Thank
Sure.
you. If you don't have any doubts, then I'll stop the streaming.
Yes. So Kenny, so we will. So you have given me two things, right? So I'll do that, and maybe in the next session, which will next week, I can.
Actually, I was just looking at the discourse. Arup sir is saying that it might be possible to take your suggestion. We will talk with the professor. If we will be grading some questions from the tutorial, then you can consider these two questions as the week 6 questions for tutorial sessions. If it is getting graded, if it is not, then we will discuss the solution. We will discuss with sir when to discuss the solution after that. Okay.
Okay. Got it. Got it.
Okay then.
All right. Thank you. Thank you so much.
Yeah. Thank you. Thank you.
Thank
I'm
you.
stopping the stream. Sorry. Yes.
No, I was just saying that. So we are ending the session now, right?
Yeah. You can
Okay.
log out.
Thank you. Good night.
Thank you.